Good morning, good afternoon and good evening to all of you wherever you are, and a very warm welcome to this DADM, which is Data Analysis and Decision Making free course under NPTEL MOOC. And as you know, this course is for total 12 weeks, contact hours is 30, which when broken down into number of lectures is basically 60 in number, because each lecture is half an hour. And we have already completed 2 weeks of classes, and as you can see on the slide, this is the 12th class, which is the second class in the third week, and 2 assignments, and coming back to the main issue, which I repeat before each class, is basically you will have 12 assignments and one end semester or final examination, and you have already taken 2 assignments. So, we will complete another 5 to go till the 15th lecture, and then you will face the or take the third assignment. So, we will discussing about the problem of the Asian paints having some raw materials, raw material 1 and raw material 2 to produce 2 outputs, paint 1 and paint 2. Similarly, in the other example, you have 2 products to make 2 raw materials to make 2 products from machine 1 and machine 2. Now, if you remember in the last class, I mentioned that how you formulate the decision variables or number of distribution variables will basically dictate how the problem will be solved. So, for the problem when if you for the Asian paints or the paint factory problem, if you take the raw materials as the variable x 1 and raw material 2 as variable x 2, then the problem formulation would be done accordingly, but the constraints concept remains same. How the constraints are basically formulated will depend on what variable you are taking. If you formulate paint 1 as raw material as decision variable 1 and paint 2 as decision variable 2, your formulation will change accordingly. Now, remember here the number of decision variables will dictate what is the dimension of the problem, because in this case it will be easier for us to basically draw the diagram, and I had shown that how the constraints can be drawn using simple linear equations, and you can find out the boundary. In the last slide which I showed the last day in the 11th lecture, it was basically how you can find out the overall feasible region inside which you have to basically find out the answer. Now, remember one thing, if I keep increasing in the same problem, the dimension can be changed depending on if you consider say for example, there are 2 raw materials to produce 5 different paints. Now, in one case if you consider the paints as decision variable, so you will basically have x 1 to x 5, in that case it is a dimension problem of 5. In other case, if you basically formulate the problem as 2 decision variables only for the raw materials 1 and 2, then it becomes a 2 dimensional problem where which you can basically plot it in a Cartesian coordinate on a graph paper. So, this I did explain in pretty much details, repeating it time and again, but we will basically try to solve the problem as it is and then basically proceed accordingly. Now, when we draw if you check the constraints, if you remember, so the constraints were in this way: 2 x 1 plus x 2 is less than equal to 8, and this 8 is basically the number of hours. So, x 1 and x 2 are the decision variables. In another case, it is x 1 plus 3 x 2 is less than 8. So, this is basically machine 1 and machine 2. For product 1, you read each product needs 2 hours in machine 1, and each product of x 2 decision variable takes 1 hour in machine 1. Similarly, product for decision variables 1 and 2 in machine 2, the respective hours are 1 and 3. So, hence it is 2 x 1 plus x 2 is less than equal to 8. So, if you want to find out which side the equation would be, you put 0 onto the left hand side of x 1 and x 2, and you find it is less than 8. So, obviously 0 would be included in the feasible region corresponding to the fact that that line is only applicable. That line means the blue one which you see here. Now, in that case, so the overall area which will be applicable in the case for the variable 1 actually would be some part of quadrant 1, some part of quadrant 2, the whole of quadrant 3 and some part of quadrant 4. When I go into say for example, the second equation x 1 plus 3 x 2 is less than equal to 8, Again 0 satisfies this. So, 0 would be a part of this equation. If you consider the whole feasible, at least the areas corresponding to equation 2, it will be some small part of quadrant 1, small part of quadrant 2, whole of quadrant 3 and some part of quadrant 4. Now, the other two constraints, as I mentioned, is the product are being manufactured and they definitely should be integer, but we are considering, again I am repeating it, we will consider them to be greater than or equal to 0. So, x 1 is greater than 0, x 2 is greater than 0. In that case, x 1 greater than 0 means only quadrant 1 and quadrant 2, x 2 being greater than 0 means only quadrant 1 and quadrant 4. So, if you basically find out the overall common area corresponding to the 4 such constraints technically, which is equation 1, equation 2, x 1 greater than 0, x 2 greater than 0, the overall area is this one, which is shown here, but I will again mark it. So, this is the area. So, this is 1. Now, the interesting part is this, and this can be extended to 3 dimension. In the 3 dimension one, if you have, so consider that I am standing in the origin and towards you is basically x 1 axis, to my right is basically x 2 axis and vertical up is basically x 3 axis. So, consider there are 3 variables. In that case, it will be a surface and a cube or a cuboid or some space would be there, which will basically use the word of hyperplanes, which would basically be the overall bounded area of this hyperplanes, which will give you the overall feasible region. So, if it is a cube, considering that, so y will get a cube in that case if x 1 is greater than 0, x 2 is greater than 0, x 3 is greater than 0 and each of x 1, x 2, x 3 are, say for example, less than or equal to 2 individually, then obviously we will have a cube of a certain dimension. Then the overall area feasible region would be all the points, infinite set of points inside the cube, but how we will basically overcome that. So, that search techniques to find out the optimum solution in minimum number of feasible region, we will go into feasible points, we will going to come to that within few minutes. Now, if you consider the area which I have just marked yellow, so that has how many corner points? 1, 2, 3, 4. One of the corner points is 0, another corner point is basically on x 2 axis, another corner point is basically on x 1 axis, another corner point is basically the common point which satisfies the equation 2 x 1 plus x 2 is equal to 8 and x 1 plus 3 x 2 is equal to 8. Now, if you remember, we had shown one picture of Karmakar. So, Karmakar's integral polynomial algorithm, I am not going to go into details, it basically states that your feasible regions is in actually infinite number, but your search space or search point should only be the corner points. So, which basically your now search technique would be such in the linear programming would only concentrate on 4 points. Now, how do you do the search? That conceptually has to be analyzed. Now, before I come to the objective function, look at this space. So, if I find out the actual points would be, I will mark it and then again erase it. So, let me go one by one. So, this point is 0, 0. This point is what? 2 x 1 plus x 2 is less than or equal to 8 and x 2 is 0. So, x 1 is 4. So, this would be 4 comma 0. The first the value is basically corresponding to x 1. When I come here, this equation becomes x 2 is 0. So, x 1 becomes 0. So, x 2 is 8. So, this would become 0 comma 8 and this equation. So, this becomes no, that is not required, sorry. So, even though I marked it. So, this point would become where x 2 would be 0. So, it will be 8 by 3 because yes, let me check, double check. So, x 1 is 0, yes, 8 by 3 and if I consider this, so this is, I will mark some other so this is 0 0, this is 083, this is 40, and this point. So, let me mark these points. This is A, I will go in a clockwise direction. This I will mark as B, this I will mark as C, this I will mark as D. So, our search will be only inside A, B, C, D. So, let me solve the equation. So, you have 2x1 plus x2 is equal to 8 and x1 plus 3x2 is equal to 8. So, if this becomes multiplying by 2, this becomes 6, multiplying by 2, this becomes 16. So, the first equation, second equation minus the first is becomes 5x2 is equal to 8. So, x2 8 by 5. So, I put up here multiplied by 5. So, it's 10x1 plus 8x2 is equal to 5 is a 40. Sorry. So, it should not be x2. So, this is already taken care. My mistake. So, let me check. This is 5 to the 10x1 plus multiply 5. So, is 8 is equal to 5 is a 40, fine. Then I go to here. So, x1 is equal to 32 by 10, which technically this also becomes 16 by 10. So, if I come here, so x1 is 32 by 10, this becomes 6, x2 is 16 by 10. So, if you want to check it, let us double check it. If you pick it here, so it becomes 32 by 5 plus 16 by, so it is 64 by 10, 16 by 10, 64 plus 16 is 80, 80 by 10 is 8. So, this is satisfied. If I go here, second equation, it is 32 by 10 plus 48 by 10, 32 plus 48 is again 80, 80 by 10 is 8. So, this is satisfied. So, I have all the coordinates. Now, only I can erase this. So, because once I click the next button, another graph will come here. So, I do not want to make it confusing. Okay. So, coming here. Now, when you do the search, there are 4 points only. So, it's for this problem is very easy. You find out the objective function, whatever the objective function is, you plug in the values of a, b, c, d separately, find out the value where the objective function maximum, report that value and find out the corresponding values of x1, x2 and your problem is solved. But the problem technically is not as straightforward. It is easy, but not as straightforward, because in a higher dimension one you will have basically almost huge number of points, and in which direction you should proceed in order to find out that you will get the optimum point or the feasible amongst the feasible point is basically the main criteria. Now, consider that, say for example, I start at 0 0 my search. Why I start at 0 0? I am going to come to that later. I start at 0 0. Now, what problem it is? It is an optimization problem. So, in the optimization problem, when you check, what you want to check is that as you change in the objective function, initially the values of x1 and x2 is 0 0. So, the objective function value is 0. Now, what you will check is that in which direction should you move the objective function such that you increase the values of either x1 or x2, considering there are only x1 and x2, or if there are more than 2 number of decision variables, consider the n number of decision variables. Considering that point, which of this x1 should you take such that the rate of change of this objective function happens as the highest rate, because it is an objective function. So, which is the maximization one. So, 1 unit change in one of these x's should basically increase the objective function the maximum. So, you will only proceed in this direction. So, if the same logic happens from the minimization point of view, obviously you will take that point where the rate of change of that objective function happens in the other direction, negative direction, the highest. So, you will keep moving in the direction. So, say for example, I move from D to C, because the consider that gives me the point that changing x1 and not x2 basically increase the objective function but the highest when you compare x1 and x2 for 1 unit of change. Then once you reach C, you basically move to B, considering that now you have basically been able to change both x1 and x2. Once you reach B, consider that the objective function is the maximum, you again, because you do not know, you have to stop, the algorithm has to stop. So, what you do is that you again move your direction from B to A, considering this is a very simple case of 4 corner points, you move from B to A. What will happen now is that the rate of change of the function would be such with respect to the objective function, because you are changing the objective function with respect to one of the variables, it will happen in such a way that the overall value of the objective function rather than increasing will start decreasing, which means that that is the point where you should stop and report that objective function and those corresponding values of x1 and x2, which will give you the maximum value. Now, this is the general way the algorithm should work conceptually, but there are other nitty-gritties and other details inside that, which we will come to that later. Now, when I am trying to solve this problem pictorially, all these details, what I said, all these details will be coming up in the theoretical part, when you basically have a tableau or table and basically proceed accordingly. But in the case when you have the pictorial one, I will basically draw it. That is why I have removed all the simple equations here. Now, the objective function is basically given, which is the green line. We will merge both these graphs together later on, or you can basically visualize how they are merged. Now, the objective function has to be drawn, because I will try to find out that in which direction the objective function keeps increasing, such that at some optimum point depending on x1 and x2 you will basically reach the maximum point. So, now consider the objective function is placed like this. Why do I place the green line in this is very simple. Find out what is the dy dx of this line depending on the values which you have. So, if you find out the values, technically the equation is given as 3x1 plus 2x2. So, considering, and that is per unit, because if you remember 3 units is coming from product 1 and 2 units are coming from product 2. So, if you consider and that is equal to z, which is the objective function, if you place that line accordingly, then the tan of this angle or the points at which x1 and x2 are touched by this line are at x1 is equal to 2, because in that case obviously you will basically have the points satisfy this equation. So, if you place that line, I am not going to draw it. So, I am just hover my electronic pen over here. So, here this green dotted lines is basically the inclination of the slope and how the objective function will look. Now, what you want in the objective function is that it should keep increasing. So, if it keeps increasing, you should move more away from the 0 0 and go deep inside the quadrant 1. So, start shifting it. But the point is that at one point of time it will leave the feasible region, which is ABCD. So, you find the point at which it leaves the feasible region, that will give you, technically that would give you the point where x1 and x2 are those values for which the objective function is maximum. And in this case you can easily find out using very simple concept, that if you see the line would basically leave the point, the feasible region at point B, hence the point B would give you the maximum value of the objective function. What I said about moving from direction D to C, C to B, B to A, or in whichever direction would basically be the conceptual framework of the algorithm based on which you are going to work. So, this is the situation. So, you have the overall region which is given. I am sure all of you have understood, but still I will highlight. So, this is again I said A, B, C, D, and this is the point for which x 1 is 3 by 2 and x 2 is 3.2 and 1.6. So, the objective function is 12.8. So, which means that you are going to produce 3.2 number of product 1, 1.6 of product 2, and the overall objective function value will be 12.8. Technically, the answers of 3.2 and 1.6 are not right because they cannot be decimal, but we will still proceed along with this point. But remember, this problem would have been perfect if it was a pen problem, because in that case you can produce any decimal values in liters, milliliters, whatever, microliters, whatever it is about the pen. So, hence we will consider x 1 and x 2 as the decision variable for the pen problem to be continuous. Now, consider the problem in such a way that the rate of revenue change due to increase in machine capacity basically happens is basically 1 hour. So, which will mean that if I change the equation, so the values which were there was 3.2, 1.6. So, let me write it down. And this value was 12.8. Let me write it down also. Now, if 1 hour change in the machine capacity is there, so what is the change we are expecting is that the value which you have initially it was 12.8. So, the value change which you will have for 1 hour change in the capacity would be 14.2. So, hence the increase which is happening for 1 unit change is 1.4. So, we are basically adding 1.4 values amount due to capacity change of 1 hour. So, that means 1 hour change basically is meaning that it is increasing from 8 to 9. So, if you basically put the equations, so if you remember equation 1 corresponding to machine 1. So, what I am trying to do is that change the capacities of machine 1 and machine 2 separately, or you can basically take them together. So, first consider machine 1 is changing. So, if machine 1 is changing, so obviously the equation becomes 2 x 1 plus x 2 is less than 9. So, in that case what happens, A remains same, B changes, which is now, let me mark it. I will not mark the values, this is A, and let me use the green color because it will be easily distinguishable by you. So, this is A, this was initially B, this was initially C, and this was initially D. Now, what happens is, now A remains A, B goes to B dash, C goes to C dash. Let me use not dash, let me use 1 2. So, it will be easier for us to, why 1 2 I am going to come to that within 2 minutes. So, this is B suffix 1, this C suffix 1 be corresponding to the change which is happening for machine 1 and 1 only. Now, in that case the values which I find out, it is 3.8 and 1.4, the maximum value of the object function is 14.2. So, 14.2 minus 12.8, which is for the first one, will give you a change for 1 unit hours is coming out to 1.4. So, this is the shadow price or the dual price for machine 1, such that the change in 1 hour per unit 1 hour, what is the extra profit you will be able to get. Similarly, when I go to machine number 2 without changing machine 1, the line will be, it should not be cluttered, I will try to draw it. I will use the red color dotted ones to basically mark machine number 2 without changing machine number 1. So, it will be like this. I am not going to mark it total in all the details. So, in this case what we will have, so let me now mark the points in green. D remains D, there is no change. A goes to A2 corresponding to change in machine 2. B goes to this point B2, and point C remains at C, it does not change. Now, if I consider the change in both machine 1 and machine 2, then obviously that point of B now becomes B suffix 1 2, because I am considering change in both machine 1 and machine 2 happening. So, similar analysis if I want to find out for the shadow price of machine 2 only, it will come out to be 0.2. So, 1.2 for machine 1 unit change, and 0.2 change in the objective value for 1 unit change in machine 2. So, obviously, you have to find out that shadow price or the conceptual rate at which you will change one of the machines in order to increase your production would definitely be coming from the highest value, which is for the case when you are trying to do the maximization problem. So, it is all green in color the points, but again I am repeating A, B, C, D is for the original problem. Then shadow price corresponding to machine 1 unit change in machine 1 is A, then B1 and C1 and D. In the next case it is basically A2, only for machine 2 is A2, B2, C remains as it is and D, and if both of them changes it is A2, B12, C1. It should be, it is basically the nomenclature is should be clear. So, A2 is basically now changing for both combination of them changing, C1 is also for both changing, and B12 is the common point. So, we will continue discussing about the concept of linear programming in details, but remember one thing, what I am mentioning is that it may be simplistic and I am trying to explain it in a pictorial way, but the concept of how you solve the problem is exactly the same what I told. You start at one point, traverse the corner points, take the decision in which direction you are going to move depending on the rate of change of the function with 1 unit change in the decision variables taken one at a time. Take the decision where the maximum change is happening for the objective function, which is a maximization problem. In the case of the minimization problem, you just do the reverse, stop at that point where the rate of change of the function does not now start decreasing, report that point and basically solve your problem. When you are trying to do it the pictorially concept I have given, and then we will basically use the concept of simple linear algebra, and that linear algebra would be very simple matrix multiplication using the Gauss-Jordan concept. I will come to that later, but for the time being I will end today. Have a nice day and thank you very much.